Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over the effects of delta H, which is the change in enthalpy of the system, delta S, the change in the entropy of the system, and temperature on the spontaneity of a process or chemical reaction. So let's get into this. So I'm going to go over four cases that you're going to run into with respect to delta H and delta S and temperature. And so let's get into these four cases. So the first case is where the enthalpy is negative and delta S is positive. So the change in entropy is positive, yet the change in enthalpy is going to be negative. So we're going to look at this equation here. So remember, this is the Gibbs free energy equation. So the change in the Gibbs free energy is equal to the change in the enthalpy of the system minus the temperature multiplied by the change in the entropy of the system. So in this case, we're looking at a case in which there is a negative change in the enthalpy of the system, and there is a positive change in the entropy of the system. And so, what do we mean by a negative change in the enthalpy? Well, that means it's an exothermic reaction, right? So it's losing energy from the system. So energy is being gained by the surroundings. Well, what happens when the surroundings gains that energy? What happens to the entropy of the surroundings? Well, the entropy of the surroundings is going to increase, right? So here we have the entropy of the surroundings increasing, and we have a positive change in the entropy of the system. So that means the entropy of the system is increasing. So, and remember, let's also remind ourselves that the entropy of the universe, right? The entropy of the universe is equal to the entropy of the system plus the change in entropy of the surroundings. So, since in this case, both the entropy of the system is increasing, and because the system is losing energy, that energy is going into the surroundings, and therefore the surroundings is going to be gaining that energy, and therefore that energy is dissipating into the surroundings. And so that's an increase in entropy. So that means that if this is the case, then the universe, the entropy of the universe is going to increase. Is going to increase here. And so that means that delta G is going to be negative. Why is it negative? Because we have a negative value for delta H, and we have a positive value for delta S, which is going to be negative, right? Negative times a positive is negative. So both of these parts of our equation is negative, which means that the delta G is negative. And remember, delta G, or the Gibbs free energy, the change in Gibbs free energy is if it's negative, that means that it is spontaneous, because remember, all systems want to go or move towards a lower potential energy. And so remember, Gibbs free energy is a measure of that chemical potential. And so to have a change which is going to be negative, meaning decreasing, then that is means a spontaneous reaction. And again, we know that the Gibbs free energy is proportional to the negative change in the entropy of the universe. So here, both of the entropies of the system and the surroundings are positive, they're increasing, which means that the entropy of the universe is increasing, which means that this is a spontaneous reaction. So remember, one of the criteria of a spontaneous reaction or spontaneous process is that it leads to the increase in the entropy of the universe, which is what we have here. So no matter what the temperature is, entropy is going to be positive for the system, and entropy is going to be positive for the surroundings because we're releasing energy into the surroundings. So this is negative. So exothermic reaction, negative release of energy into the surroundings. Okay, so here's an example where we have 2 N2O gas breaking down into nitrogen and oxygen And here we have the enthalpy, the standard enthalpy of the reaction is negative 163.2 kilojoules, right? So we have the delta H of the reaction is negative. So that's releasing energy into the surroundings and increasing the entropy of the surroundings. And we also have an increase in the entropy of the system, because you can see that we start with 2 moles of the reactant, and we're getting 3 moles of the product. So we're increasing the moles of gas during the reaction. So an increase in the moles of gas is an increase in entropy, right? So if you remember, the more particles you have at a given energy, remember the microstates, macrostates. So here, more particles, more moles means more possible microstates, or ways to arrange your particles in energetically equivalent ways. So more particles means more ways to arrange those particles. So this is a good example. So this will always be a spontaneous reaction at all temperatures. All right, what about case number 2? Case number 2 is where we have a delta H is positive, so therefore the change in enthalpy of the reaction is positive, meaning it's increasing in energy, which means it's endothermic. It's pulling in energy from the surroundings. So it's taking energy from the surroundings, and what that means is that the surroundings is going to have less entropy. So you are taking entropy away. So the surroundings is decreasing in entropy because it's an endothermic reaction. And we have a negative delta H of the system. So the entropy of the system is decreasing as well. So here we have a positive value for our delta H. Again, that's because it's absorbing energy. It's an endothermic process, and therefore taking energy away from the surroundings, and therefore the entropy of the surroundings is going to decrease. And here we have a negative value for our delta S. So that means that the entropy of the system is decreasing. So if you're decreasing the entropy of the system, and you're also decreasing the entropy of the surroundings, given that this is negative and this is negative, then that means the change in the entropy of the universe is negative, which is not favorable to a spontaneous reaction. So that means that under these conditions, where you have a negative delta S of the system, the entropy of the system, and you also have a positive enthalpy of the system, meaning that it's absorbing energy from the surroundings, and therefore the surroundings is going to decrease in entropy. So both are decreasing, so therefore the entropy of the universe is negative. The change in the entropy of the universe is negative, and therefore this is not going to be spontaneous. So under all conditions, so also mathematically, you can see, okay, this is positive, and so this is delta S is negative, and then negative and negative is positive. So that means that you have a delta G that is also going to be positive. So a positive plus a positive gives you positive. And so remember, in the same way that the change in entropy of the universe is an indicator or a criterion for spontaneity, you need a positive increase. You need an increase in the change in the entropy of the universe. You need a negative change in the Gibbs free energy. But here, there's no way to get a negative, because this is positive, and a negative times a negative is positive. So a positive plus a positive is always going to give you a positive value for the change in Gibbs free energy, and a positive value is a non-spontaneous reaction or process. So here, under these conditions, under this case, delta G is always positive at all temperatures. So that means that this is going to be a non-spontaneous reaction at all temperatures. And an example of this would be where you have oxygen forming ozone. So here you have 3 oxygen gas molecules, and then you go to 2 ozone molecules, and you can see that the delta H of the reaction is positive. And you can see that the entropy of the system, the reaction, is positive as well, because you're decreasing the number of moles. You're going from 3 moles of oxygen to 2 moles of oxygen. So again, remember, more particles means more microstates, more ways to arrange the particles in a way that they're energetically equivalent to each other, right? So here we're getting less particles. So less particles means lower entropy. And so both the entropy of the system is decreasing, and you have a positive value of your reaction. And again, that means it's absorbing energy, taking energy away from the surroundings, and therefore lowering the entropy of the surroundings. And so this would be a non-spontaneous reaction under all temperatures. Okay, so I'm going to go over the next 2 cases in just a moment. So give me just a moment. Okay, welcome back. So now to do cases 3 and 4. So in case 3, we have delta H, the enthalpy is negative, and delta S, the entropy is negative as well. So remind ourselves again that when the delta H or the enthalpy is negative, that means that the system is losing energy to the surroundings. And what happens when energy is lost to the surroundings? Entropy of the surroundings increases. And so entropy of the surroundings is going to increase with a negative delta H. But also you have a negative delta S of the system. So the system is decreasing in entropy, while the surroundings is going to increase in entropy. So there's different signs here. One's increasing, one's decreasing. And so here it's going to depend on temperature whether or not the process is spontaneous or not. And so what you want to think about here is with regard to temperature. So what happens at temperature with respect to the entropy of the surroundings? If you remember, in the surroundings, or our units of entropy, entropy has the units of joules per Kelvin. And so remember, absorbing or emitting heat to the surroundings or absorbing heat from the surroundings is going to have less effect on the entropy of the surroundings at higher temperature, right? So in this case, we have a negative enthalpy, so energy is giving out to the surroundings, and that's going to increase the entropy of the surroundings. And that's what we want. We want more of an increase, more of an effect on the entropy of the surroundings. And so, but here we have a negative entropy of the system. So when are we going to have a greater effect on the entropy of the surroundings? That's going to be at high temp or at low temperature, because at high temperature you have less of an effect. So remember, high temperature in Kelvin means that this entropy is smaller, right? And again, using the analogy of giving like $1,000 to a poor person, right? Someone who doesn't have money, giving them $1,000 is really gonna improve their or affect their financial situation. Same way as if I take $1,000 away from a poor person, that's really going to affect their financial situation. But giving $1,000 to a millionaire or taking $1,000 from a millionaire doesn't really have any effect really on their financial situation, right? So same thing with the temperature into the surroundings, right? So at a high temperature, it's already full of heat, so adding a little bit more heat is not really going to affect the entropy of the surroundings. But if you at low temperature, you add a little bit of heat, that's going to have a dramatic effect on the entropy of the surroundings. So here, since our delta S is negative, we want an overall positive delta S for the universe, which is your delta G, right? So here, uh, if we're releasing, if this is negative, meaning we're releasing energy into the surroundings, we want that to have a greater effect. So we want at low temperature. So at low temperature, that emitting of heat into the surroundings is going to have a greater effect. It's going to on the entropy. It's going to have a greater effect on the entropy of the surroundings, and therefore, overall, it's going to have increase the entropy of the universe at low temperatures. So we're going to get a negative value of our delta G, and you can see that in the equation. So if this is negative, right, and we have a negative and a negative here, that means that this is going to be positive. So in order to get this to be negative, we need this portion, this positive part, to be as low as possible. So if we decrease T, then this part will be low enough where then the two added together is going to be negative. But at high temperature, negative and negative is positive. So at high temperature, this value is going to be very large and positive, so much so that adding these together, you're going to end up with a delta G of positive, which is not spontaneous. So again, so this is going to be a spontaneous at low temperature, but non-spontaneous at high. And here's an example where the reaction or the process of going from liquid to solid water, right? So to go from a liquid to a solid, you got to remove heat from the water. So the delta H is negative. And so you're going from liquid to solid. That's a decrease in the entropy of the system because you're going from molecules that can move around and have many degrees of freedom and many kinds of energy like rotational energy and translational energy, all the way it's going to become a solid, and it's just going to have vibrational energy. So it's less types of energy, less places to put the energy, so less entropy. And so this process is only going to be possible at low temperature, as we know, 0 degrees lower, below 0 degrees. Above 0 degrees, it's not going to be spontaneous. It's going to be non-spontaneous. Okay, what about case number 4? So this is where you got a positive enthalpy and you've got a positive entropy of the system. And so what does a positive enthalpy means? It means that the system is absorbing heat from the surroundings. So in this case, it's taking energy from the surroundings, and therefore the entropy of the surroundings is going to decrease because it's losing that energy, right? And but in this case also delta S is positive, the entropy of the system is becoming positive, so that's going to be positive. And again, we want to have the entropy of the universe to overall increase. So our system entropy is increasing, but our surroundings entropy is decreasing. So they're going in opposite directions again. So now it's going to be a matter of which one is greater. And so here we have a delta H of positive. So that means that it's gaining energy again from the surroundings, and that means that the surroundings is losing entropy. But like what we said before is at high temperature, that taking away of energy or giving energy to the surroundings is going to have less of a dramatic effect on this entropy of the surroundings. So here we want this part. So at high temperature, right? At high temperature, that taking away of the energy of the surroundings is not going to have as dramatic effect on the entropy. So if we had this at low temperatures, we can keep that entropy loss at a minimum, and then we have that positive entropy gain in the system. And so if we can keep the entropy loss at a minimum, such that the positive entropy gain of the system overrules or is predominant, then we can get a negative value here for our Gibbs free energy. So you can see that here with the positive value for this, and we got a negative and a positive, so this value is going to be negative. So we want this value to be negative, and this negative value be greater than the positive value here, so that we can get a negative value here. And that's going to happen at high temperature. So when temperature is high, this whole thing is going to be a large negative value. And then with adding that with the positive value, if this is larger than this, then the negative value is going to be carried over. So this is going to make this negative. And so again, at positive, so this is delta G is going to be positive at low temperature and therefore non-spontaneous at low temperature. But at high temperature, where that absorbing of energy doesn't affect the entropy of the surroundings as much, negative, that's going to have a negative, that's going to give you a negative Gibbs free energy. And so that's going to be spontaneous at high temperature. And so here's an example of H2O liquid going to a gas. So when you go from liquid to gas, you're increasing the entropy of the system, because remember, at a liquid, the liquid molecules the water molecules are close together, and so when you make them into a gas, they spread out, and then they can disperse the energy of the molecules further and more abroad. So it's more entropy. So the system here is gaining entropy from going from a liquid to a gas. But you can see here that the enthalpy change is positive. So it's absorbing energy from the surroundings in order to put that energy into the molecules to get them to spread out and move and break free of those intermolecular forces. And so in that case, absorbing the energy from the surroundings is going to decrease the entropy of the surroundings. And so in this case, this is going to be at 100 degrees. At high temperature, this is going to be spontaneous. Below 100 degrees, it's not going to be spontaneous. So I hope this is a good introduction or explanation of how your delta H and your delta S of the system can affect the entropy, or I'm sorry, the spontaneity of your process, the Gibbs free energy. If this was helpful in any way, if you enjoyed this video, please make sure you hit that like button there, subscribe to my channel, hit that notification bell up there so you can be notified by other videos I put out. Put a comment down in the comment section below. Let me know what you think. Ask me questions. I'd love to hear from you. Thanks for joining me, and have a great day.